Hi everyone. Welcome to the utilization of additive manufacturing at Virgin Orbit. My name is Oluseun Taiwo. I'm an advanced manufacturing engineer on our propulsion team. And a little later in this conversation, my colleague Dayle Alexander is going to share some of the applications of additive manufacturing in some of our projects. Let's get started. Why AM at Virgin Orbit? Well, at Virgin Orbit, we are constantly pushing the bounds of how orbital class rockets are flown and built. Just look at our system for an example. And so additive manufacturing actually allows us to increase performance of the components propulsion-wise and structurally-wise on our vehicle while decreasing cost, lead time, complexity, and part count. At Virgin Orbit, we utilize two types of additive manufacturing techniques. The first is powder bed fusion. We use a layer-by-layer powder bed approach in which the components and features are sintered using a laser and are subsequently solidified. We also use Direct-Energy Deposition. This is a free-form fabrication process that uses a coaxial laser and powder is blown into a melt pool to create features. So next, I'm going to talk about some applications for PBF printing. Really, internally, the most important and common ones are for thrust chambers and injectors. The reason for this is because DMLS is exceptional at producing really great features of sizes that are tiny. So for example, in injectors, at the bottom you have, depending on the design, you might have really tiny holes that would really be struggled to be machined features, whereas in printing, you can actually print that fairly easy. And kind of the similar mindset with thrust chambers as well. You have cooling channels that run maybe the whole length, right, of a thrust chamber, and being able to then manufacture that in one go is actually like almost impossible. But with printing, right, we can design and manufacture it pretty much, whatever those sizes are. There's some limitations, but I think we do a great job internally of understanding that and then being able to push right up to the boundaries of that. Also, with PBF or powder bed fusion process, we have in-house capabilities, but then also we have amazing vendors that we work with too. And so combining those two streams of manufacturing actually allows us to respond quite quickly to being able to really iterate quickly, but then also maybe if there's testing that comes up last minute for stuff, we can do that fairly quickly and respond awesomely. So yeah. Next, we're going to talk about the directed energy deposition process and some applications attached to that. And so at Virgin Orbit, we actually have adopted and provide a really unique, amazing hybrid DED process. So when I say hybrid, I mean kind of like additive and then also subtractive manufacturing in the same machine. And so effectively, we can build quite honestly, whether it's structural jackets for a thrust chamber perhaps, or even different types of cladding techniques. We can really do that in one machine and subtract as well, which means we have a single setup. And one of the best things about a single setup means that you can kind of continue off where you've started and stopped. And also you have the ability, really, if you mess up, you can kind of go back and fix that. And so this is awesome because it allows for us to be able to combine previous materials that would be great together but aren't really possible to combine and manufacture parts together. And so that gets us excited, right? Because we can really get a performance upgrade by playing with different materials and combining them together. So I will say that DED and powder bed fusion are not plug and play systems, right? There's a lot of materials science and development that goes into actually producing test coupons and really making sure that we are producing the best material possible if we are going to produce products with those processes. So yeah, up next, my colleague Dayle Alexander is going to talk about more of the applications using these systems.
Thanks, Oluseun. Like he said, my name is Dayle, and I work in the propulsion department at VO. I'm a design and analysis engineer, and I work with several different projects that we have here that utilize additive manufacturing. We have, like he talked about, several different ways that we can do additive manufacturing. We have the DED option, we have the powder bed option, and we try to incorporate as many options as we possibly can to get the best parts we possibly can. we can work with nickel alloys and copper alloys and steels. And as a design engineer and analysis engineer, that really helps us be able to get the best parts that we want. We can determine the kind of material that we want for all of our strengths and analyses that we use to in our combustion device analyses. Yeah, so on this slide here, you can see a couple of photos. The two on the top show us kind of like an old prototype manifold that we made a while back. These kinds of things are very helpful to us. Things like manifolds that are hard to machine on the inside without having to mate them together with another part and seal them together. When you are able to print those two sections together that normally would have been a mate with seals, if you can print them all as one part, it reduces leak paths in the system. So we work with a lot of fluid systems with high pressure, and that's really beneficial for us there. Also, really complex geometries are able to be printed better than they would be on a regular manufacturing process. For example, this manifold has, you can see kind of a big, large section there that you wouldn't have been able to access at all in a regular CNC machine. So we're able to print stuff like that, which really helps us as well. The picture on the bottom shows one of our chambers that I'll talk about in more depth a little bit later. But chambers, combustion chambers in a rocket engine usually utilize cooling channels for some kind of cooling fluid to go through and cool down the metal on the inside where all the combustion and hot gases are happening. And usually in this process, you have to machine your liner first and then coat the outside with a metal jacket is what it's called. And you have to machine all of your individual channels and then coat the outside. What Oluseun was saying with our hybrid machine that allows subtractive and additive manufacturing is that you can combine those processes together. So you could DED print your jacket on the outside of a chamber, and then without removing the part, you could then machine additional features onto that. And that really cuts down on processing time. Sometimes we have to send parts out to different vendors to do both of those different things and spend a lot of money. And if we don't need to do that, that's great for us. So yeah, those are just a couple of the benefits that I've listed here of additive manufacturing. One project I'd really like to touch on was a great project that we did with NASA a couple years ago, where we did just that. And NASA 3D printed a copper liner for a combustion chamber, and we put it in our additive subtractive manufacturing machine, and we DED printed a jacket on the outside for the chamber. And then we were able to add the manifolds on the top and the bottom of that chamber. And then we hot fired it at NASA and got some really great data there. You can see these photos on the right here are pictures of the completed chamber on the test stand at NASA Marshall Space Flight Center. And we saw some really good results with this. It was a regular LOX kerosene propelled engine and saw chamber pressures up to 1,000 psi. Here you can see on this next slide some of the photos from the manufacturing process. I'll start on the left here, so you can see they used powder bed fusion version of 3D printing to make the copper chamber. This was done at NASA, and then they sent it to us, and we did the DED machining of the outer jacket. And then the completed chamber went back to NASA and went through hot fire testing. This little diagram you can see on the right there shows each of the processes in the DED chamber. So you can see we've got the bare copper part here on the upper left in photo A, and then the coating on the outside being done by the DED machine, and then photo C is final machining done on the outside of the chamber after the coating, the jacket coating, and then photo D shows the final completed product. And that's just a really cool photo of one of the hot fires. It's a very, very neat project. And then if anybody wants any more information on that, ntrs.nasa.gov, and then very long number there. Okay, so switching gears just a little bit, I really wanted to touch on this great project that Virgin Orbit was able to do earlier this summer. Because of the COVID pandemic, we were actually in a really unique position to design and manufacture a low-cost, easy-to-build system that can be used in emergency situations for patients in a hospital that could need a ventilator during the COVID crisis. We manufactured about 600 units, and we sent all of our designs over to different countries so that other people could make these products themselves. And we were able to use a little bit of our printing knowledge to benefit us in this project. We didn't use any 3D printing in the actual, the final product components. And this is because we know that we wanted this to be very reproducible in other countries and for other companies. And not everyone has access to 3D printing technologies, so we wanted to make those machinable, all of the parts that are in the actual ventilator itself. However, we had an opportunity when we were working with the acceptance test of each ventilator unit to use our small ABS printers to print out several couplers in the patient airway system. The patient airway system is just the tubing that goes from the ventilator to the patient, really low pressure air system. But it turns out we couldn't get some of the couplers that we needed in time to start testing right away. So what we did was we printed a bunch out of plastic to use during our test procedures instead. And that way we were able to print a whole bunch at a time. We were able to print a whole bunch of different sizes. And it really benefited us and enabled us to keep working even when we couldn't get something off the shelf really quick. So that's a great example of how not even a metal printer can be beneficial sometimes. We also use our plastic printers for printing prototypes, just kind of seeing how big something actually is in real life instead of on the computer, or what it might look like or how it might fit up on assembly. So we actually use our plastic printers quite a bit. Yeah, so that's a pretty good introduction to our ventilator project. If anybody's interested in that a little bit further, you could go to virginorbit.com/ventilators to learn more about that. Yeah, so that's about all of the info that we have. Thank you, everybody, for listening in, and keep printing.